Hi, my name is Mckenna, and I am a member of Dr. Beng's research group that focuses on organic chemistry research. So my presentation is on the selective oxidation of sulfur-embedded cyclic amides. The thiodiazine derivatives shown in the figure above my head constitute the core of several pharmaceuticals and display a broad spectrum of biological activities, including anti-HIV, and anti-cancer properties. The NS heterocycles, which this research is focused on, are engaged in several selective fragment group processes, including oxidation of sulfoxides, sulfones, and epoxides. Sulfur-containing heterocyclic compounds are prevalent in nature and biological systems, and specifically we'll look at the NS heterocycle, such as 4-thiodizine, and how it exhibits a diverse range of biological activities, including antifungal, antioxidant, and anti-inflammatory, and anti-HIV, and many other properties. So my research, previously research has revealed that the anhydride imine reaction shown in A between the thiodigallic anhydride 1 and the imine of type 2 proceeds effectively under thermal conditions and affords functionally as thiamophoric acids, such as 3 demonstrated in A, and B is our current study that seeks to unveil the preferred mode of reactivity of disulfide-embedded anhydride 4 when exposed to aryl amides of type 2A, either their aryl or alkynyl forms. We also desired to elaborate the ensuring products 5 and 6 in their aryl and alkynyl form as well as their oxidized variants shown in 7 and 8. The initiated studies towards the construction of 4-thiodiazine derivatives and subsequent fragment growth by attempting to find suitable directing group-free conditions for the annihilation reaction above my head, shown in the reaction scheme. The reaction optimization was eventually carried out, and it was established previously that 2-methyl tetrahydrofluorine, or 2-METHF, outperforms other reaction media such as benzene or chlorobenzene or toluene, and the reaction medium is quite friendly given the well-documented merits of 2-METHF, including that it readily phase separates from the aqueous layers, and it is obtained from furfural, which originates from a renewable seed stock and is easily oxidized. The amides harboring both electron-neutron and electron-rich groups and electron-deficient aryl groups recently aryl groups react completely, shown in 5A and 5G and 5H. The ortho-substituted arenes are amiable in this annihilation period in annihilation protocol, albeit with slight decrease in efficiency, shown in 5F and 5H. The halogenated arenes are well tolerated in 5G, which bodes well for the late stage, the diversification of the halogen group, and may be utilized as a functional handle for the cross-coupling purposes. Specifically, if you look at 5H and the CHF3 group, it enjoys a privileged role because of its incorporation often enhances efficiency by promoting electrostatic interactions with targets, improving cellular membrane permeability, and increasing robustness towards the oxidative metabolism of the drug. The trimethylfluoridated product 5H is obtainable in a satisfactory yield. Following the successful construction of 2-thionyl 4-thiodizines, the next step is to prepare their 2 alkynyl conjugates. The amiability of the 1,3-azidines of type 2 to annihilation reaction with 4 is explored, and 4 reacts chemioselectively with the several substituted 1,3-azidines and affords the allylic 4-thiodizines depicted in the figure. The chemioselective formation of 6 indicates a scenario whereby the 1,2 addition pathway outcompetes the 1,4 addition pathway. In the synthesis of potential drug candidates, scalability is often a significant factor as it serves to provide efficient amount for clinical tests. A potential benefit aspect of this methodology is therefore scalable in nature, as we previously saw with the 5H and 6A. This has set the stage for post-diversification studies. Sulfoxides and sulfones are common structural groups found in natural products and pharmaceuticals. The direct oxidation of sulfides is arguably one of the most straightforward, atom economical, and reliable ways for the preparation of sulfoxides and sulfones. However, the selective oxidation of sulfides is non-trivial, and stoichiometric quantities of toxic and strong reagents are often employed. These methods unfortunately mar harsh reaction conditions and poor chemical activities and environmental contamination problems. Thus, we aim to develop a water-tolerant conditions for the switchable synthesis of sulfoxides and sulfones, which implies Selective-4 as the oxidant and water as both reaction medium and oxygen source, shown in the figure above, as it promotes green chemistry, which is desirable in many organic chemistry reactions. The evidence depicts the 13 carbon NMR diagram for the overlaid compound. And the 13 carbon NMR is measured in parts per billion and looks at the significant groups at specific points. And I know it's hard to tell, but if you look at the values, the aromatic rings are on the 150 from 150 to 100, meaning the tallest and largest peak, and the group that has the carbon double bonded to an O bonded to an N, i.e. this part, is the part represented here. In short, the strategic development of dithiazole anhydride as an alternative to metacopic acid, a liquid with a strong, unpleasant odor, has led to a modular and practical synthesis of benzylic and allylic 4-thiodizing by engaging the aforementioned anhydride in a formal 3,2 cycloaddition with aryl amides or 1,3-azodimines. The criteria for efficiency and versatility are of paramount importance in modern-day synthetic chemistry. And these studies have met these benchmarks. Since many existing cyclization strategies for 4-thiodizing tend to exhibit poor generality, require protecting group manipulations, and depend on specific directing groups, we anticipate that the current approach will sidestep these limitations and greatly expand the structural space for discovery. Thank you for listening to my presentation, and I want to thank the chemistry department for their help and support. I want to thank Dr. Beng for being an amazing mentor, and I want to thank our research for funding this presentation.
Good morning. I am going to talk about a little bit of the research I did over the last couple of years about mixed monolayer gold nanoparticles and their interactions with bovine serum albumin. So to begin with, what is a nanoparticle? Well, a nanoparticle is an engineered nanoparticle is generally defined as being less than 100 nanometers in at least one dimension. So how small is that? It is very, very small. For comparison, the width of a human hair, the diameter of a human hair is 17,000 to 180,000 nanometers. And so again, nanoparticles, 100 nanometers or less, very, very tiny. Usually when we synthesize those, they're synthesized in two parts. The core is composed of a metal like gold or silver or something like silica, sometimes polymers. And that produces the unique properties that you get at a nanoscale. So unlike bulk material, gold, for instance, you're all familiar with what that looks like in your jewelry. Nanoparticles that are made of gold, they actually appear red in solution. They have some really interesting light scattering qualities to them. In order to protect that size of the nanoparticles, you have to surround each nanoparticle with a capping agent of some sort. A lot of the time that is an organic ligand, and it is bonded to the surface of the nanoparticle and then protects it either by steric hindrance, so size, they can't bump into each other, or by electrostatic repulsion, so like charges deflecting one another away. That layer then becomes kind of the interface between the nanoparticle and the environment around it. So if we want to use nanoparticles for therapeutic or diagnostic uses, if we want to inject them into you in some way, then we need to know what happens when they're in your bloodstream or other biological environment. And it's pretty well known and accepted that as soon as a nanoparticle enters your bloodstream, proteins, which are very sticky, like to adsorb onto it. They form a shell that we call the protein corona. And that shell then, that becomes the new interface between the nanoparticle and the environment around it. And that determines things like whether the immune system responds to it or whether a cell will take it up or not. There are a lot of forces at play in the formation of that protein corona, in the formation of that shell. They're not entirely understood, so they're the subject of a lot of research. Currently, it is believed that electrostatic forces are the primary director of that formation. So positive charges repel and, or like charges repel and opposite charges attract, and either charge likes a neutral surface. And so that is one of the ways that people are trying to figure out how that works so we can direct the formation of the protein corona and in turn direct what the body does to the nanoparticles. Now, one of the most or the most abundant protein in blood serum is albumin. Albumin is about 5 nanometers in diameter in its native conformation, and it is intrinsically fluorescent. It has 2 tryptophan residues that if you excite at 280 nanometers, then they light up, give off light at another wavelength, and that's a pretty handy quality. Bovine albumin is very similar to human albumin, so it's used as a model protein for a lot of studies. When the albumin is close to a nanoparticle, the electron plasmon on the surface of a nanoparticle will absorb the energy that would otherwise be given off as light. So we call that quenching. That means that if the albumin is stuck to a nanoparticle, it is not fluorescent. It just absorbs the light and nothing happens that we can see. So the question is, if electrostatic interactions are the primary driving force, how can we adjust those? Could, for instance, using 2 different ligands in your monolayer cap of different charges, could that affect the formation of that protein corona? Now, gold nanoparticles, in addition to some of the nice light scattering qualities that they had and their ability to quench fluorescence of albumin, have a lot of interesting applications in therapeutics and diagnostics. They make a great contrast imaging agent. It is hoped that they can be used to deliver drugs directly to tumor tissue. One of my favorite applications is that they will turn light into heat. So if you inject nanoparticles and they accumulate in tumor tissue and you can put the right wavelength of light into the tumor, that will heat up the nanoparticles. They give off heat. That heat kills the tumor tissue around it without damaging all of your healthy tissue that you're wanting to protect. So gold nanoparticles are also easily synthesized, generally at room temperature, just in a tube or that you see here, or a beaker or a flask. and they can be synthesized directly. So by that, I mean everything can just be put into the same solution. You get what you want out of it. And that includes what I'm going to show you here. So this is the chloroauric acid that has the gold. The gold is reduced by the sodium borohydride over here into the nanoparticles. The capping agent are these Bunte salt ligands right here. So this sulfur here bonds to the surface of the gold and kicks off this part of the molecule here. So what you get is the sulfur and then whatever organic group you wanted as reaching out into space away from the nanoparticle. Nanoparticle synthesis is also the most fun looking thing we do. This moves fast, so don't blink. Oh, and you can see it's red, like a dark red. It's very nice. So I did synthesize my gold nanoparticles with a mixture of two ligands. I used this one right here, which you see in green. It's MEEE, and it is neutrally charged at all pHs. I also used MHA right here, which is negatively charged at 7.4, which is the pH in your bloodstream. I gave them a 90-10 mixture of these two when I synthesized them, but they self-assembled themselves in a 75-25, roughly 75-25 ratio, with 75% the neutrally charged ligand and 25% the negatively charged ligand. Now, how do we find out how that changes the interactions between these nanoparticles and the albumin? Well, we use that fluorescent property of albumin that I talked about a minute ago. So what you see are, I'm just going to show you the green one. Here at the top, this is the fluorescence spectra. So this is the light emitted along these wavelengths by the albumin when I excited it at 280 nanometers. So I gave it light at 280 nanometers, measured what came out. The top line right here is where there were no nanoparticles in the solution. So this was the albumin fluorescing the way it would, unperturbed by anything else. And then as I added increasing amounts of nanoparticles, that fluorescence decreased because of those interactions that I talked about where the nanoparticles quenched the fluorescence of the albumin. And that rate of decrease says a lot about how much the albumin likes the nanoparticles and wants to stick to them. We call that the affinity. One measure of that affinity is the association constant, the binding constant. So if you graph the intensity of the emissions here, right, how high up they are on these plots, if you graph them against the concentration of the nanoparticles, and the associations are static, the quenching is static, which means the nanoparticle and the albumin, when they stick to each other, they stay that way, then you get a linear relationship. And the slope of that line tells you the affinity of the albumin for the nanoparticles. So the steeper the line, the more the albumin likes the nanoparticle. And the flatter the line, the less that it likes the nanoparticle. So comparing them, just to review, blue is negatively charged, yellow is neutral, green is a mixture of the two. It's not immediately apparent just when we look at these graphs, but when we do the math, the negatively charged and mixed ligand nanoparticles, the albumin have the same affinity for those two. And in both cases, that was more than it had for the neutrally charged nanoparticles. So it did not stick as well, as much to the neutrally charged nanoparticles as it did to nanoparticles that had any negative charge whatsoever. I used the same fluorescence data to plot it a little bit differently in a hill plot. This was to test for binding cooperativity. Cooperativity is when the presence of one albumin bound to the nanoparticle encourages or raises the chances of additional molecules of albumin binding. And that again is a function of the slope of this particular graph. So if the slope is greater than 1, then binding is cooperative, and it was greater than 1 in all cases for all 3 of my nanoparticles, regardless of that surface charge. This is a little different than is found in the literature. Different studies of a variety of nanoparticle sizes and core materials and surface chemistry. Sometimes it's cooperative, often it is not. I suspect that in this case, if you notice, the size of the albumin and the size of the nanoparticle were the same. They were both about 5 nanometers. And I think that because of that, an albumin on one side of the nanoparticle is seen, for lack of a better term, by something on the other side of the nanoparticle. It is interesting that the mixed ligand nanoparticles behaved mostly like the negatively charged ones rather than somewhere in the spectrum between them to reflect that subtler change in surface charge density. But that is what I found. And then binding cooperative in all cases, again, as I said. And just as a bonus, this is an electron microscopy image of some of my nanoparticles, 100 nanometer bar on the bottom there. So they're very, very tiny. And that's a really good picture of them. I was very happy. I said it was baby pictures. I'm not sure my advisor thought that was as cute as I did. Anyway, do we have any questions? Yes, Dr. Beng. The Hill plot or the Stern-Volmer plot? The Hill plot? I plotted it according to the way Hill plots are plotted. So basically, this reflects how many docking stations on a nanoparticle are available versus how many have an albumin docked into them. And that relationship ought to be linear if the interactions are static. If it had not turned out linear, then yes. And in fact, in the Stern-Volmer plot, that was kind of the test of that. If these lines had not been linear, you don't think they're linear? Because you're seeing right here. Okay. That's an interesting idea because there are some papers that reflect that nanoparticles can induce the aggregation of protein, which is actually the aggregation you're talking about, as opposed to aggregation of nanoparticles that we generally try to avoid. And that would coincide with the cooperative binding, because cooperative binding can be an effect of a misfolded protein interacting with other proteins and causing additional misfolding, which would then cause aggregation. So yes, I think for the purposes of a Hill plot, you do want to force a linear plot on it to determine what the slope is. But I agree that a very mild parabolic line would probably fit there also. Yeah. Other questions? I don't think I see any online. All right, thank you very much.
Hi, thank you. So in my project, in this study, we show that we can in fact use HepG2 cells as a model for non-alcoholic fatty liver disease solely with excess sugar instead of excess sugar with excess fat. But first, why should we even study liver disease? In this table, it compares different ages, genders, and ethnicities of people in the United States with non-alcoholic fatty liver disease. And you can see that while there's trends with there being more non-alcoholic fatty liver disease patients who are a little bit older, or possibly more obese patients have non-alcoholic fatty liver disease, it does seem to be a trend that this is something that can affect anyone. This is something that anyone can have. More specifically, whenever we compare this across the entire American population, 1 in 3 of US citizens are having this disease. But this is not just a United States problem. This is an increasing problem globally. This map above me shows the amount of NAFLD patients with diabetes in particular globally. And this is an important thing to specify because liver disease is going to lead to heart disease. It's going to lead to insulin resistance and obesity. So these are important factors to remember when we talk about non-alcoholic fatty liver disease. But what is it? Excess sugars in the diet synthesize fats. And whenever the liver is making too many fats or lipids, or de novo lipogenesis is occurring, then this probes the issue of hepatic steatosis, or excess storage of fats. And this becomes pathologic and induces lipotoxicity. And liver disease leads to serious complications that are irreversible. It leads to cirrhosis and hepatic liver cancer. But first, what does it look like? The phenotype of someone with liver disease has a liver with a high fat concentration, fibrosis, glucose intolerance, and elevated fructose 1P levels and reduced beta oxidation. Specifically, it's really important to remember that this leads to irreversible consequences. It leads to cirrhosis and liver cancer, where at this point, you need a new liver. So my study focuses on the dangerous precursors to cirrhosis and liver cancer, particularly steatosis and NASH, which is non-alcoholic steatohepatitis. Particularly in my study, I look at the fat content with oil red O assays and reduced beta oxidation with WST assays. And before any of this was done, I compared the concentrations of cell seeding with crystal violet assays. An important thing to remember before we get started is that excess dietary sugars lead to increased levels of growth hormones in fatty liver disease. Seen here are my HepG2 cells under a microscope. So first, I ask the question, do excess sugars alone drive cell growth or cause cell death? Crystal violet assays were done in order to count the amount of cells, to measure the number of cells. Here, we see that excess sugars aren't really changing the rate of growth. We see, did it show? Yes. Okay. I show that 3 different levels of hexoses, so physiological glucose at 5 millimolar, excess glucose at 25 millimolar, and excess fructose with 25 millimolar fructose and 5 millimolar glucose without growth factors don't have a significant change in the rate of growth, which is all normalized back to the day 1 seeding concentration. But what happens when we add growth factors? More crystal violet assays were done to answer this question. And as you can see here, again, we have the 3 hexoses. However, they're in all growth factors. They have FBS, insulin, and TNF alpha, which again, doesn't show a change in the rate of growth. So what do we have right now? We have excess glucose and excess fructose having the same amount of cells. So what's the difference? What's the problem? So then I ask, do excess sugars increase intracellular lipid accumulation? Is there a difference in lipid accumulation between fructose and glucose? Oil red O assays measure lipid accumulation. So this is how we're going to test it. Here, we have the 3 hexoses with 4 different levels of growth factors. No growth factor, FBS and insulin, FBS and TNF alpha, and FBS and insulin and TNF alpha. All normalized back to the no growth factor. Here you can see that there is an increase slightly with the insulin, which makes sense. I'm sorry. However, let's look a little bit closer to the two larger groups on the side. Here you can see that the TNF alpha groups are increasing lipid storage with excess sugar, whether or not insulin's included. So why is that happening? Here we see that the amount is the same for fats and fructose, but you just saw a difference in the last slide. What's happening is even though there's an increase with TNF alpha, it's the same for fructose and glucose. So again, we have the same amount of cells and the same amount of fat. What's happening? So now I ask the question, do excess sugars increase mitochondrial function? Do different growth factors increase mitochondrial function? This was tested with a WST8 assay, which measures mitochondrial dehydrogenase enzyme activity. Excess fructose here shows lower mitochondrial activity, even though all glucose is showing twice as much mitochondrial activity, except in one group, the TNF alpha group. So why is that happening? Does TNF alpha signaling interfere with the mitochondrial function? How are these results connected? So with fructose, we have a reduced mitochondrial function. With glucose, we're having twice as much mitochondrial function. But why? Increased TNF alpha increases gene expression of fatty acid synthase and acetyl-CoA carboxylase, which we show in the oil red O assays have more lipids with TNF alpha, which follows. Then the WST assay shows reduced mitochondrial activity. A decrease in healthy mitochondria also follows. Lastly, we show that with excess fructose, there's more TNF alpha, which then signals the stress and lipogenic pathways, which creates more trans factors, which are creating the uncoupling protein UCP4, which with extra expression is then creating more reactive oxygen species, which can be measured in a glutathione assay. So what's next? Glutathione assays to measure the redox balance. Thank you. And all of my references. Questions? Yes. That's actually really interesting, and I could barely hear you, so just to make sure I have the question right, you're asking why I used HepG2 cells for my model? Okay, so in literature, and the references showed in the last slide, there's a lot of rat and human models that show the exact same things that I was showing with my assays. We have increased lipid accumulation, decreased mitochondrial function, and what my presentation is really showing is that we can use HepG2 cells. It's really not inferred that we can use HepG2 cells, but at the end of it, it's saying, yes, HepG2 cells are a valid model, and we can continue to compare these to perhaps aldose knockout cells, which other people in my lab are working on. And this can go forward as a good control and can be a model for non-alcoholic fatty liver disease. Yes? So first, we have these flasks that I grew stock cells in, right? And so they grow up to a certain point where I believe I showed the HepG2 cells underneath the microscope, right? And in this, Then they become trypsinized, so they get lifted off the plate with a series of chemicals and incubated and resuspended in media and plated across the 96 wool plates you see here. Then stains are added, and they, depending on the assay, for example, crystal violet assays measure the number of cells. So it's staining the cells so that it can be measured in a spectrometer in order with the wavelength. It shows a quantitative amount of cells rather than just looking at it and saying, well, that is darker. Does that answer your question? So here, for example. Okay, yeah. Okay, so all of these are normalized because whenever they do get plated in a 96 wool plate, you want to have the same amount of cells in each plate to have an appropriate measurement of whether or not there's more cells in the plate or more lipids in the plate or more mitochondria being used. And if it's not normalized back to the concentration, like a singular 1 concentration, you don't know if that's just me messing up a pipette or if that's actually scientifically what's happening.